All right, so this is going to be the last video on quantum mechanics and quantum chemistry. We'll start out with some more problems, review problems. What are the allowed quantum numbers for an electron for an electron that is in a 3D orbital? Okay, and so let's do that uh, uh, together right now. Now, one thing to note is, you can look at the 3D block on the periodic table. So let's pull up the periodic table. Where did I put it? Periodic table. Here you go. Periodic table. So 3D block, right? We said the D block, or any D block, is 10 wide from scandium to zinc. So there's going to be 10 different answers for this, basically 10 different electron configurations. Okay, so let's write out what those quantum numbers would be. So we know each element has a different set of quantum numbers, right? And if there's 10 elements on the periodic table, that means 10 sets of quantum numbers. Okay, so we're talking about 3D here. So that means n is going to be equal to 3 for all of these. Okay, so we're going to have 10 with n equals 3. 5, 6, 7, 8, 9, 10. Okay, and what does D mean? D means, recall, that D means L equals 2. Remember, L equals 0 equals S? Remember the chart, guys? If you have S, P, D, and F, those each have L values, 0, 1, 2, 3. So we're D, so L equals 2. So all of these 10 electron configurations are all going to have L equals 2. Okay. What about M sub L? M sub L can range, M sub L can go from minus L to positive L, right? So this is where things are going to get interesting. We can have -2, -1, 0, 1, and 2. So I'm going to put M sub L equals +2. And I know that there's going to be 2 spins, right? There's going to be a spin, because spin up is +1/2 of electron, and spin down is -1/2. But then I can also have the other M sub L's with all the other different values, right? So I could have -2, -1, 0, and the 2 positive ones. And all of those can have +1/2 or -1/2. So these would be my 10 different answers. Okay. I'm writing this out just to be super clear to you guys. If you explain this in words, or the multiple choice problem explain this in words a little bit better than writing it out, but I just wanted to be very explicit so you could see all the different combinations that there are. Okay, so that's for that problem. Let's go back to the other problems. How many electrons can be in the same orbital? Okay, 2 electrons. That's by definition spin up, spin down. Okay, what is the electron configuration orbital diagram for phosphorus? Okay, so let's look at phosphorus on the periodic table. It's going to be 1s2, 2s2, 2p6, 3s2, and then 3s3. Now we could write that as bracket neon, 3s2, 3p3. That would be a shorthand way. So I'll do all those 2 different ways, and we still have to write the orbital diagram. That was part of the question, right? The orbital diagram. Okay, so let's go back to the whiteboard, and let me just erase that right whiteboard. Okay, and so this is phosphorus. phosphorus electron configuration. The longhand electron configuration we said was as follows. 3p3. The shorthand configuration with the noble gas, nearest noble gas, is neon. So we can say bracket neon. That takes care of all this. And then we would say it's like this. Okay. But if we're going to write a complete orbital diagram, we have to basically write all of the different orbitals. So these core orbitals, core electron orbitals, we can write out and just pair them all up because they're all filled. Okay. But then we have to be careful once we get to the 3p, right? Because we have 3 electrons. These are valence electrons now. We have to follow Hund's rule. So with the seats on the bus rule, they have to be in separate ones. So make sure, you know, you got that right there where you're not pairing them up. If you can put them in different orbitals of the same energy, they will go into different orbitals of the same energy. That's more energetically favorable, and that's indeed what the ground state is. All right, let's go back to the slides here. Order filling. This is sort of a mnemonic that some people use to figure out, you know, to memorize basically this 1s, 2s, 2p, 3s business. I don't use this. They do this thing with arrows and they write this out. I don't use this. I just use the shape of the periodic table. And that's what I suggest you do. I think it's a lot easier. You can see the S block is 2 wide. You can see the P block is 6 wide. Since you're getting the periodic table on the exam, you can do this. The D block is 10 wide. The F block is 14 wide. Just use the shape. I did mention there's some exceptions to the rule. So look at chromium. This is just kind of for your own interest. I'm never going to test you or on these, as I mentioned in the last video. You expect it would be argon, bracket argon, 4s2, 3d4. Actually, it's 3d5, 4s1. Why? Books will tell you different things. The real answer is quantum mechanics tell you that. The math tells you that. It's too complicated for us to go over. Why memorize it? I think it's silly. We're not going to memorize it. Copper turns out to also be something that you don't expect. There turns out to be a whole mess of exceptions, okay? Luckily, most of them are not exceptions. Otherwise, it wouldn't really be a rule to the first place, right? We couldn't use the word exceptions. So let's not worry about the exception. Okay. Isoelectronic, we said, are ones that have the same electron configuration. These 3 species all have the electron configuration of bracket krypton. They have 36 electrons.